Part 1, Introduction to Magnetic Tests. Magnetic testing is part of the widely used family of electromagnetic non-destructive testing. The theory and practice of electromagnetic techniques are discussed elsewhere in the NDT Handbook. When used with other methods, magnetic tests can provide a quick and relatively inexpensive assessment of the integrity of ferromagnetic materials. Magnetic particle testing is, in fact, a variation of flux leakage testing that uses particles to produce indications. Because of the prevalence of tests specifically using particles, magnetic particle testing is usually treated as a separate method by industry and in the literature. The term flux leakage testing, also called diverted flux testing, is then meant to exclude tests with particles. The magnetic circuit and the means for producing the magnetizing force that causes magnetic flux leakage are described below. Theories developed for surface and subsurface discontinuities are outlined, along with some results that can be expected. Industrial uses. Magnetic testing is used in many industries to find a wide variety of discontinuities. Much of the world's production of ferromagnetic steel is tested by magnetic or electromagnetic testing techniques. Steel is tested many times before it is used, and some steel products are tested during use for safety and reliability and to maximize their length of service. Production testing. Typical applications of magnetic flux leakage testing are by the steel producer, where blooms, billets, rods, bars, tubes, and ropes are tested to establish the integrity of the final product. In many instances, the end user will not accept the delivery of steel product without testing by the mill and independent agencies. Receiving testing. The end user often uses magnetic flux leakage tests before fabrication. This test ensures the manufacturer's claim that the product is within agreed specifications. Such tests are frequently performed by independent testing companies or the end user's quality assurance department. Oil-field tubular goods are often tested at this stage. In-service testing. Good examples of in-service applications are the testing of used wire rope, installed tubing, or retrieved oil-field tubular goods by independent facilities. Many laboratories also use magnetic techniques along with metallurgical sectioning and other techniques for the assessment of steel products and the prediction of failure modes. Steps in magnetic testing. There are 4 steps in magnetic testing. 1. Magnetize the test object so that discontinuities perturb the flux. 2. Scan the surface of the test object with a magnetic flux sensitive detector. 3. Process the raw data from these detectors in a manner that best accentuates discontinuity signals. And 4. Present the test results clearly for interpretation. The following discussion deals with the first step, producing the magnetizing force. Magnetic particle testing. Principles. Magnetic particle testing is a non-destructive method of revealing surface and subsurface discontinuities in magnetizable materials. It may be applied to raw materials such as billets, bars, and shapes. During processes such as forming, machining, heat treating, and electroplating, and in testing for service-related discontinuities. The testing method is based on the principle that magnetic flux in a magnetized object is locally distorted by the presence of discontinuity. This distortion causes some of the magnetic field to exit and re-enter the test object at the discontinuity. This phenomenon is called magnetic flux leakage, or MFL. Flux leakage is capable of attracting finely divided particles of magnetic materials that in turn form an outline or indication of the discontinuity. The intensity or the curvature of the magnetic flux leakage field is critical in causing particles to remain held at an indication. One of the objectives of magnetic particle testing is to detect discontinuities as early as possible in the processing sequence, thus avoiding the expenditure of effort on materials that will later be rejected. Practically every process from the original production of metal from its ore to the last finishing operation may introduce discontinuities. Magnetic particle testing can reveal many of these, preventing flawed components from entering service. Even though magnetic particle testing may be applied during and between processing operations, a final test is usually performed to ensure that all detrimental discontinuities have been detected. In welds with a tendency toward delayed cracking, there may be a specified time delay between the completion of welding and the final test. The test itself consists of three basic operations. 1. Establish a suitable magnetic flux in the test object. 2. Apply magnetic particles in a dry powder or a liquid suspension. And 3. Examine the test object under suitable lighting conditions, interpreting and evaluating the test indications. Capabilities and limitations. Magnetic particle testing can reveal surface discontinuities, including those too small or too tight to be seen with the unaided eye. Magnetic particle indications form on an object surface above a discontinuity and show the location and approximate size of the discontinuity. Magnetic particle tests can also reveal discontinuities that are slightly below the surface, depending on their size. There are limits on the ability to locate subsurface discontinuities. These limits are determined by the intensity of the applied field and by the discontinuity's depth, size, type, and shape. In some cases, special techniques or equipment can improve the test's ability to detect subsurface discontinuities. Magnetic particle testing is for ferromagnetic materials only. It cannot be used on non-magnetic materials, including glass, ceramics, plastics, or such common metals as aluminum, magnesium, copper, and austenitic stainless steel alloys. In addition, there are certain positional limitations. A magnetic field is directional and for best results must be perpendicular to the discontinuity. This generally requires magnetizing operations in different directions to detect discontinuities. Objects with large cross-sections may require a very high current to generate a magnetic field adequate for magnetic particle tests. A final limitation is that a demagnetization procedure is usually required following the magnetic particle process. Knowledge of limitation can be helpful to managers, supervisors, and personnel outside non-destructive testing who require general information on the magnetic particle testing process. It may also be helpful for introductory studies by individuals already using magnetic particle testing or those preparing for advanced training in the technique. Magnetic field theory. Magnetic domains. Materials that can be magnetized possess atoms that group into magnetically saturated regions called magnetic domains. These domains have a positive and negative polarity at opposite ends. In macroscopically unmagnetized material, the domains are randomly oriented, usually parallel with the crystalline axes of the material, resulting in zero net magnetization. When the material is subjected to a magnetic field, the domains attempt to align themselves parallel with the external magnetic field. The material then acts as a magnet. Figure 2 illustrates the domain alignment in non-magnetized and magnetized material. Magnetic poles. A magnet has the property of attracting ferromagnetic materials. The ability to attract or repel is not uniform over the surface of a magnet, but is concentrated at localized areas called poles. In every magnet, there are two or more poles with opposite polarities. These poles are attracted to the Earth's magnetic poles and therefore are called north and south poles. Figure 3 can be duplicated by placing a sheet of paper over a bar magnet and sprinkling iron particles on the paper. It shows the magnetic field leaving and entering the ends or poles of the magnet. This characteristic pattern illustrates the term lines of force used to describe a magnetic flux field. There are a number of important properties associated with lines of force. 1. They form continuous loops that are never broken, but must complete themselves through some path. 2. They do not cross one another. 3. They are considered to have direction, leaving from the North Pole and traveling through the air to the South Pole, where they re-enter the magnet and return through the magnet to the North Pole. 4. Their density decreases with increasing distance from the pole. And 5. They seek the path of least magnetic resistance or reluctance in completing their loops. When a bar magnet is broken into two or more pieces, new magnetic poles are formed. The opposing poles attract one another as shown in figure 4. In If the centerpiece in figure 4 is reversed so that the similar poles are adjacent, the lines of force repel one magnet from the other. If one of the bars is small enough, the lines of force can cause it to rotate so that unlike poles are again adjacent. This illustrates the most basic rule of magnetism. Unlike poles attract and like poles repel. Types of magnetic materials. All materials are affected to some degree by magnetic fields. Matter is made up of atoms with a positively charged nucleus surrounded by a field of clouds or negatively charged electrons. Surrounded by a field or cloud of negatively charged electrons. The electron field is in continual motion, spinning around the nucleus. When the material is subjected to a magnetic field, the electron orbits are distorted to some degree. The amount of this distortion, or the corresponding change in magnetic characteristics, when subjected to an external magnetic field, provides a means of classifying materials into three main groups: diamagnetic, paramagnetic, or ferromagnetic. The term diamagnetic refers to a substance whose magnetic permeability is slightly less than that of air. When a diamagnetic object is placed in an intense magnetic field, the induced magnetism is in a direct opposite to that of iron. Diamagnetic materials include mercury, gold, bismuth, and zinc. Paramagnetic describes a substance whose permeability is slightly greater than that of air or unity. When such materials are placed in an intense magnetic field, there is a slight alignment of the electron spin in the direction of the magnetic flux flow. This alignment exists only as long as the paramagnetic material is in the external magnetic field. Aluminum, platinum, copper, and wood are paramagnetic materials. Ferromagnetic materials. Ferromagnetic substances have a permeability that is much greater than that of air. When placed in an external magnetic field, the magnetic domains align parallel with the external field and remain aligned for some period of time after removal from the field. Ferromagnetism can only be explained via the domain theory. Paramagnetic and diamagnetic materials do not contain such domains. This continued alignment after removal from the external field is called retentivity and can be an important property in some magnetic particle testing procedures. Some examples of ferromagnetic materials are iron, cobalt, nickel, and gadolinium. Sources of magnetism. Permanent magnets. Permanent magnets are produced by heat treating specially formulated alloys in an intense magnetic field. During heat treatment, the magnetic domains become aligned and remain aligned after removal of the external field. Permanent magnets are essential to modern technology. Their applications include magnetos, direct current motors, telephones, loudspeakers, and many electrical instruments. Common examples of permanent magnet materials include alloys of aluminum, nickel, and cobalt, copper, nickel and cobalt, copper, nickel, and iron, and cobalt and molybdenum. Supermagnet materials such as neodymium, iron boron, and samarium cobalt are now common. Magnetic field of the Earth. The planet Earth itself is a huge magnet, with north and south poles slightly displaced from the Earth's axis. This displacement results in a slight deviation between geographic north and magnetic north. As a magnet, the Earth is surrounded by magnetic lines of force as shown in Figure 5. These lines of force make up what is sometimes called the Earth field, and they can cause problems in both magnetizing and demagnetizing of ferromagnetic test objects. The Earth field is weak, on the order of 0.03 mt or 0.3 g. Movement of ferromagnetic objects through the Earth field can induce slight magnetization. This is a problem in aircraft, where magnetized components can affect the compasses used in navigation. Similarly, demagnetizing can be difficult in certain objects. If certain objects If certain objects, usually long shafts, are not oriented from east and west during the demagnetization process. Well, I'll read that again. Similarly, demagnetizing can be difficult if certain objects, usually long shafts, are not oriented from east to west during the demagnetization process. Mechanically induced magnetism. Cold working of some ferromagnetic materials, either by forming operations or during service, can magnetize objects. When mechanically induced magnetization occurs as a result of forming operations, it can be removed by subjecting the magnetized objects to a routine demagnetization process. It can be difficult to remove mechanically induced magnetization resulting from cold working. Disassembly is usually impractical, and demagnetization must be accomplished using portable yokes or cable coils. The operation is complicated when other ferromagnetic components are near the magnetized object. The demagnetizing operation can magnetize adjacent objects, and a sequence of demagnetizing operations must then be performed. Part 3. Magnetic flux and flux leakage. Circular magnetic fields. The most familiar type of magnet is the horseshoe shape, shown in Figure 6a. It contains both a north and south pole, with lines of magnetic flux leaving the north pole and traveling through the air to re-enter the magnet at the south pole. Ferromagnetic materials are only attracted and held at or between the poles of a horseshoe magnet. If the ends of such magnet are bent so that they are close together, Figure 6b, the poles still exist and the magnetic flux still leaves and re-enters at the poles. In such a case, however, the lines of force are closer and more dense. The number of lines of flux per unit area is called magnetic flux density and is measured in Tesla or Gauss. If the magnetic flux density is high enough, ferromagnetic particles are strongly attracted and can even bridge the physical gap between the poles that are close enough together. The area where the flux lines leave the pole, travel through air, and re-enter the magnet is called a magnetic flux leakage field. When the ends of a magnet are bent together and the poles are fused to form a ring, the magnet no longer attracts or holds ferromagnetic materials. There are no magnetic poles and no flux leakage field. The magnetic flux lines still exist, but they are completely contained within the magnet. In this condition, the magnet is said to contain a circular magnetic field or to be circularly magnetized. If a crack crosses the magnetic flux lines in a circularly magnetized object, north and south poles are immediately created on either side of this continuity. This forces a portion of the magnetic flux into the surrounding air, creating a flux leakage field that attracts magnetic particles and forms a crack indication. Longitudinal magnetization. If a horseshoe magnet is straightened, a bar magnet is formed with north and south poles. Figure 7a. Magnetic flux flows through the magnet and exits or enters at the poles. Magnetic poles can be thought of as occurring wherever field lines enter and leave a magnetized object. Ferromagnetic materials are attracted only to the poles, and such an object is said to have a longitudinal field or to be longitudinally magnetized. If these magnetic flux lines are interrupted by a discontinuity, additional north and south poles are formed on either side of the interruption, Figure 7b. Such secondary poles and their associated flux leakage fields can attract magnetic particles. Even if the discontinuity is a very narrow crack, it will still create magnetic poles that hold magnetic materials, which are the magnetic flux leakage field is still finite. Read that again. Even if the discontinuity is a very narrow crack, it will still create magnetic poles that hold magnetic materials. The magnetic flux leakage field is still finite. Magnetic field intensity. The intensity of a flux leakage field from a discontinuity depends on several factors. 1, the number of magnetic flux lines. 2, the depth of the discontinuity. And 3, the width of the discontinuity's air gap at the surface, the distance between the magnetic poles. The intensity and curvature of the leakage field determines the number of magnetic particles that can be attracted to form a test indication. The greater the leakage field intensity, the denser the indication, so long as the magnetic flux leakage field is highly curved. Subsurface discontinuities. A slot, such as a keyway on the backside of an object, creates new magnetic poles that distort the internal flux flow. If the slot is close enough to the surface, some magnetic flux lines may be forced to exit and re-enter the magnetized object at the surface. The resulting leakage field can form a magnetic particle test indication. Size and intensity of the indication depends on 1. The proximity of the slot to the top surface, 2. The size and orientation of the slot, and 3. The intensity and the distribution of the magnetic flux field. A similar effect occurs if the discontinuity is completely internal to an object. Figure 8 is an illustration of a keyway on the far side of a bar, and Figure 9 illustrates a mid-wall discontinuity. Effect of discontinuity orientation. The orientation of a discontinuity in a magnetized object is a major factor in the intensity of the magnetic flux leakage field that is formed. This applies to both the surface and internal discontinuities. The most intense magnetic flux leakage field is formed when the discontinuity is perpendicular to the magnetic flow. If the discontinuity is not perpendicular, the intensity of the magnetic flux leakage field is reduced and disappears entirely when the discontinuity is parallel to magnetic flux flow. Figure 10 illustrates the effect of discontinuity orientation on the intensity of the magnetic flux leakage field. Formation of indications. When magnetic particles collect at a flux leakage site, they produce an indication visible to the unaided eye under the proper lighting conditions. Tighter magnetic flux leakage fields create the ideal conditions for particle attraction. The force on an individual particle being given by the product of terms involving the particular Tighter magnetic flux leakage fields create the ideal conditions for particle attraction. The force on an individual particle being given by the product of terms involving the particle shape, the local value of the field intensity, and a term involving the local curvature of the magnetic flux leakage field. Particles then tend to align end to end in this field. The stronger the ability to hold the particles, the larger the indication. 4. Electrically induced magnetism. Circular magnetism. When an electric current flows through a conductor, such as a copper bar or wire, a magnetic field is formed around the conductor. The direction of magnetic lines of force is always 90 degrees from the direction of current flow. When the conductor has a uniform shape, the flux density or number of lines of force per unit area is uniform along the length of the conductor and uniformly decreases as the distance from the conductor increases. Because a ferromagnetized object is a large conductor, electric current flowing through the object forms a circular magnetic field. This magnetic field is known as circumferential magnetization because the magnetic flux lines form complete loops in the object. A characteristic of circumferential magnetic fields is that the magnetic flux lines form complete loops without magnetic poles. Because magnetic particles are only attracted to and held where flux lines exit and enter the object's surface, indications do not occur unless a discontinuity crosses the flux lines. Inducing circular magnetization in a test object. Figure 12 illustrates a method for inducing a circular field using a magnetic particle testing unit. The test object is clamped between the contact plates so that electric current can pass through it. When tubes are tested by passing a current through them, the magnetic flux is zero at the inner surface or axis and its maximum at the outside surface. The inside surface is often equally important when testing for discontinuities. Because a magnetic field surrounds a conductor, It is possible to induce a satisfactory field in the tube by inserting a copper bar or some other conductor through the tube and passing the current through the bar. This method is called internal conductor magnetization. Figure 13 indicates a method employed for circular field inspection of short parts. For longer parts, such as steel tubes, an insulated metal rod is run along the bore of the tube, exciting it with a high current. The rod should not touch the inside of the tube, and the tube should be placed on wooden planks to isolate it from the ground. These measures should eliminate arc burns from the magnetizing current grounding. Magnetic field direction. The magnetic lines of force are always at right angles to the direction of the magnetizing current. One way to visualize the direction of magnetic flux is to imagine the conductor held in your right hand, with the thumb extended in the direction of the current flow. When your curved fingers then point in the direction of the magnetic flux flow. This is known as the right hand rule. Longitudinal magnetization. Electric currents can induce longitudinal fields in ferromagnetic materials. The magnetic field around a conductor is formed oriented lengthwise direction by forming the conductor into a coil. The magnetic field around a conductor is oriented lengthwise direction by forming the conductor into a coil. The right-hand rule shows that the magnetic field at any point within the coil is in a lengthwise direction. When a ferromagnetic object is placed inside a coil carrying an electric current, the magnetic flux lines concentrate themselves in a longitudinal direction. An object that has been longitudinally magnetized is characterized by poles close to each other, close to each end where the field lines leave and enter the test object to form continuous loops around the associated current. When a longitudinally magnetized object contains a transverse discontinuity, a leakage field is produced that attracts magnetic particles and forms an indication. Figure 17 illustrates a typical coil found on magnetic particle test systems used to locate transverse discontinuities. Multidirectional magnetization. When testing for discontinuities in different directions, it is standard practice to perform two tests, one with circular magnetization and the one with longitudinal. Two or more fields in different directions can be imposed on an object in rapid succession. When this is done, magnetic particle indications are formed when discontinuities are favorably oriented to the direction of any field. Such indications persist as long as the rapid alternations of current continue.